Right, good morning everybody. If I could start with a mea culpa. I made a grave error yesterday. I departed from my notes because I'd finished what I wanted to talk about with 5 minutes in hand, and thought it'd be quite jolly to try to plot the eigenvalues, the two solutions, as a function of mass ratio. That was a very stupid thing to do. I've since concluded there is no way of presenting that plot which makes the underlying physics any clearer, and what I did was riddled with errors, so please completely ignore it, and I'm not going to revisit it. Now, I want to do several things this morning. First, I want to compare what I did yesterday, the general case with unequal masses, with the equal mass case, just to pull out the similarities and differences. And then I want to talk about energy, and as a preamble to that, I will look at one simple inhomogeneous problem, which is relevant to one of the problems on the problem set as well. So I'm going to make a comparison chart of the what I'm calling the general case with unequal masses and the equal mass case. So the equation of motion is very slightly different. So in general, it's mass matrix times d2x by dt squared equals minus kx. In this case, it's just mass, the single mass, times d2x by dt squared equals minus kx. That is as similar as it could be. You could, if you wanted to, you could view that as m times the unit matrix, in which case they're identical. The normal mode solution is exactly the same in both cases. X equals f of t c. So that's common. The effect of substituting that is to yield the two equations, and here there is a difference, and the difference here is a difference of choice because I wanted to stick with the definitions that you'd already learned. So the eigenvalue equation in this case is kc equals lambda c. That's the usual form of it. And the eigenvalue equation in this case is kc equals lambda mc. And that's the usual form of that eigenvalue equation. But that has a consequence because the lambdas are now, and this lambda has dimensions of spring constant, this lambda has dimensions of frequency squared. So the other equation, the equation for f, is different. This one here is d2f by dt squared equals minus lambda over m f, whereas here we have d2f by dt squared equals minus lambda f. So that's, I could have defined lambda differently at an earlier stage, and then this eigenvalue equation would have had a kind of non-standard format. But because I was doing that first, I wanted to keep that in its standard form. So then the general solution in terms of arbitrary constants is the same. Is x is sum over I ci ai cos omega I t plus bi sine omega I t. So that's the same in both cases, but in terms of initial conditions, it's different because dot products work differently in the two cases. So on the simple case, it's x is sigma over I Ci transpose x of naught cos omega I t plus Ci transpose v of naught over omega I sine omega I t, all of that times Ci over Ci transpose Ci. So you can't really write, perhaps I should have done these on two separate boards. And then here we've got x. All the dot products have the mass matrix in between them, so it's very similar, but we have Ci transpose m x of naught cos omega I t plus Ci transpose m v of naught over omega I sine omega I t, all of that times Ci divided by Ci transpose m Ci. So this dot product here and here acquire m's in the middle, and the dot product in the denominator acquires an m. So obviously it would be very artificial to introduce m's into here to make it look the same as this. So I've just done it I've developed each theory separately in the most natural way, but that does mean that they don't touch at as many points as they could have done if I'd developed the theory in a slightly unnatural way. So that was the first thing I wanted to do, was just to run through a comparison of those two cases. The next thing I want to do is to look at a simple inhomogeneous problem, which is the result of applying an external force to the system. And the external force I'm going to deal with this system without the lower mass. So that's the two equal mass equal spring system there. And I'm simply going to apply a force down on the lower mass. Okay? So the equation of motion is now, you can see that it's still got motions that are available to it, but I'm interested in the equilibrium, the static condition. Okay, so how do we handle that problem? Well, the equation of motion is m d2 x by dt squared. Actually, because the mass isn't going to play any role, let's treat it as though the masses were unequal. Equals minus kx. So this is mass times acceleration. This is the force from the spring system. I'm just going to add in the forces on the two masses, F, where F is the force on mass 1, the force on mass 2. And in this case, the force that I'm applying is 0 on the top mass and Ka on the lower mass. Okay? And in order to solve that, we're going to look for time-independent static equilibrium, which simply involves equating the forces. And so we have Kx equals F. Now, all the matrices we've encountered so far, when we've wanted to solve equations of that sort, have been singular because we've been looking at eigenvalue problems. This matrix, however, is not singular, and we can simply invert that as x equals K inverse F. So let's just work that out. So K is K times 2 minus 1 minus 1, 1. And so K inverse is K inverse times 1, 2, 1, 1. divided by the determinant, which is 2 minus 1, which is 1. So x is K inverse 1, 1, 1, 2, 0, Ka, which is K inverse 2 Ka, which is A 2A. So what happens when we do that is the displacement of the lower mass is twice the displacement of the upper mass. That means that the spring's extensions are equal, which means that we have static equilibrium all the way up the chain. The force that I'm applying at the bottom is being applied to the support at the top, and it's in equilibrium all the way up. Now, the syllabus contains a different type of inhomogeneous problem, which I'll return to next week, where f is time dependent and we want to solve the time dependent equation. They call that response to a sinusoidal driving force, and that's an item on the syllabus, and I'll do that next week. But having done that little problem, I'm now in a position to talk about energy. So obviously you're very familiar with the idea that a single mass on a spring can be thought about in terms of an exchange between kinetic energy and potential energy, and the sum of these two is always the same, is constant, is conserved. Now, this more general system has the same types of energy available to it. It's got kinetic energy and potential energy, but it's not a simple exchange from one to the other, because it's also, what's also happening is, as is evident in this example, is that energy is being transferred from one mass to another. So if we set up a very simple set of initial conditions here, which is just one mass moving, so there's energy in the first system, and then over time it gets transferred to being in the other system, in the second pendulum. And if I keep talking nonsense for long enough, then eventually the first one will come to a rest. So the energy transfers, there are more types of energy transfer involved, and so it's not quite so straightforward. But the formalism is essentially the same. So the two types of kinetic energy involved are the kinetic energy, which I'm going to call, actually what do I call it? What does it say? All right. Well, I can't call it K, so I'll have to call it T. T, sigma over I, a half mi vi squared. So let's deal with the unequal mass case, because there's no penalty in doing that at this stage. So if we wanted to write that in terms of vectors, then we'd have to do something like 1 sigma over I. But this is a sum over particles. So if I do that summation with matrix algebra, I don't need the summation anymore. So that is 1/2 V transpose MV. Okay? So that's 1/2 V1 V2 M1 naught naught M2 V1 V2, and if we multiply that out, we get that. Obviously, in the equal mass case, it looks cosmetically different. It will be a half, and the M comes here, and then we just have V transpose V. So that's essentially the same. However, an interesting thing happens if we substitute a normal mode solution. So if we substitute x is sigma over I, Ci f of t, Fi of t, where Fi is the usual Ai cos omega I t plus Bi sine omega I t. Okay? So now this summation is now summing over modes. So if I substitute that solution into this equation here, which is really my result at this stage, substitute that, and I'll just do this for 2 modes so that I can write it out explicitly. 1/2, and then we have C1 transpose F1 plus C2 transpose F2, M C1 F1 plus C2 F2, and these have to be the time derivatives, so these are the dots. Okay. I mean, I should have written out the equation for v, which is the time derivative of that, of course. So if I just expand that out, I get 2 terms involving C1 transpose MC1 F1 dot squared plus C2 transpose MC2 F2 dot squared, which are the ones where you take that with that. And then the 2 cross terms are C1 transpose MC2 F1 dot F2 dot plus C2 transpose MC1 times the same thing, F1 dot F2 dot. And now something rather interesting happens. These are very clearly not 0, they're positive definite. These, on the other, are in the form of the orthogonality relation between 2 vectors belonging to different eigenvalues. So these terms are actually 0, which means that the kinetic energy has split up into terms relating to each mode. So it's 1/2 sigma over I, modes again, 1/2 Ci transpose Ci Fi dot squared. So the kinetic energy is a sum of kinetic energies associated with each mode. So the kinetic energy splits up into a sum over modes. So now let's look at the potential energy. So we have to take some arbitrary configuration of the system and work out how much we've changed the elastic energy. There is, of course, quite a lot of elastic energy stored in the springs already because it's sagging under gravity and so on. And there is also the energy due to gravity. But we're ignoring all of that. We're simply looking at the change in the spring we're going to integrate the force on the particle. So what I want to find is the potential energy V with particle 1 at when the So when particle 1 is at x1 and particle 2 is at x2. And the way I'm going to approach that is by starting from the equilibrium position and considering a succession of positions with the same ratio of displacements in the two masses at all times until I get to the desired final position. Okay? I'm going to integrate the work done to get from the equilibrium position to the final position. Okay? So I'm going to write x as x1 times 1 alpha, where alpha is x2 over x1. Okay? So I'm going to consider a set of intermediate positions x equals y times 1 alpha for y going from 1 to x1. Okay? So as y varies from 1 to x1, these positions give you the positions that I was just displaying. At each position, the restoring force is minus kx. Right? Which means that the applied forces, in order to have to be the negative of that, plus kx, because there was never any acceleration in the system. It just moved it with infinitesimal slowness from the equilibrium position to the final position, and so there was never any acceleration of the system. It was all done very slowly and smoothly. So the work done so that's F is F dot dx, which is, so this kx here is k1 alpha y, and this is F dot dx, where dx is 1 alpha dy. So this delta w, well, so the work done is being stored as the potential energy. So this is actually the change in the potential energy in that increment, which is therefore F, well, one of these had better be transposed, doesn't it? Let's transpose that one, which is 1 alpha k 1 alpha y dy. So that's the work done to get us from x to x plus delta x. And so the total work done, which is stored as potential energy, is the integral from 0 to x1 y dy multiplied by the constants 1 alpha k 1 alpha. Which is now y dy is so that's a half y squared, which is a half x1 squared. So it's a half x1 squared 1 alpha k 1 alpha. And if I distribute 1x in x1 into that vector and 1x1 into that vector, that becomes a half x transpose kx. So the potential energy is always a half X transpose K X. And that's the corresponding expression to the T, which is just at the top of the board there. So the total energy, while we've got that, let's do exactly the same modal decomposition. So let's substitute X is sum over modes Ci Fi, and obviously exactly the same thing is going to happen. V will contain terms like a half C1 transpose K C1 F1 squared, and similarly a half C2 transpose K C2 F2 squared, and it will contain cross terms like a half C1 transpose K C2 F1 F2 and a half C2 transpose K C1 F1 F2 as well. Now, again, these terms here, what was I doing zeros with purple? Where's my purple gone? Lost it. Can't do it. Oh, there it is. If we just look at this bit here, C1 transpose KC2, well, KC2 is C1 transpose lambda 2 MC2. That's the eigenvalue equation. And so here we've got lambda 2 times C1 transpose MC2. But that, we already remarked, is the form of the orthogonality relation. That's 0, which means these two terms are both 0. And this also splits up into terms relating to each mode. So the potential energy, V, is sigma over I, where this time this is modes, C1 transpose. Actually, we could do the same trick here. We can do KC1 is lambda MC1, so that's C1 transpose MC2 lambda, CI transpose MCI lambda I Fi squared. So that's the modal energy for the potential energy. And that means that we can write a total energy, E, is a half. Well, first of all, I'll write it in terms of x's, so that's x dot transpose mx plus x dot, so, well, sorry, I wasn't doing those with dots, was I? V1 transpose mv plus x transpose x transpose kx. So that's the general form of the potential energy in terms of positions. But interestingly, it splits up into modal energies. E is sigma over I, EI, where the modal energy, EI, is the sum of this box here and where's me? That box there. So this one involves Ci transpose MCI multiplied by F dot Fi dot squared. And this one involves Ci transpose MCI times lambda F squared. So it's very simple. EI is Ci transpose MCI times F dot squared plus lambda F squared. There are slight differences if we worked it through for the equal mass case, because the m's would appear in this equation in a slightly different place. They'd appear as a multiplying factor, and here we'd have, and because the lambdas are defined in a slightly different way, that would also appear slightly differently. So I'm not going to go through that, but what I will do is just observe that the differential equation that's satisfied by f is d2f by dt squared equals minus lambda f. So lambda is effectively omega squared, so you could also write that as omega squared. And in that form, it's then exactly the same for both cases. So we can either have the mass in there as a matrix or out here as a constant. And that equation preserves the value of this bracket. So how do I prove that? I multiply both sides of this equation by f df dt. So I get d2f by dt squared df by dt plus lambda f df by dt equals 0. I then observe that both of those terms are perfect differentials. This is the I do beg your pardon, there's a half missing there. Just slipping up. Right, so this term here is the differential of a half df by dt squared. This term here is the differential of a half f squared with respect to time, and so when I integrate with respect to time, I get a constant of integration, which is the modal energy. So a half times, well, no, it's not the modal energy. It's a constant of integration. It's a constant of integration c. So this bracket here is constant, which means that the modal energy is constant. So the total energy of the system is made up of energies associated with every mode, or each mode, and those modal energies remain constant through the motion. So the exchange of energy, we have exchange of energy between potential and kinetic going on within each mode, but the modes themselves are basically uncoupled aspects of the system which just pursue their way independently. So there is a fixed modal energy which is set into the system at the outset. So if we take that initial condition of the one I was just analysing, where I just pull this lower mass down, if I work out the modal energy in this position, now of course in this position the modal energy is only potential energy because it's not moving, but I can work out if I write the displacements in terms of modes, so I analyse the two displacements into the eigenvectors of the two modes, and then I can compute the modal energy just using the potential energy form, using this equation here, and that gives me the modal energy in each mode, which is then fixed for the rest of the motion. So there's a certain energy in mode 1, a certain energy in mode 2 at this point, and those values are remaining constant in the subsequent motion. And so that's one of the problems on the problem set, is precisely that calculation. And so what you have to do is to analyse the initial displacement, and the initial displacement we worked out was A to A. We have to analyse that as sigma AI CI, and then we can once we know that, we can then substitute the amplitudes for the modes that we get into this equation here. So Fi is Ai cos omega I t, and we're going to do it at time equals 0. So Fi is just Ai, and F dot is 0. So the total energy is just E is sigma over I, 1/2 C I transpose. Is this an equal mass case? Yes, I rather think it is. M Ci transpose Ci times omega squared Ai squared. So that's the expression for the modal energies, and that will work through to give you the answer. And in fact, one of the eigenvectors for this system is 1 and 1 plus root 5 over 2, which is 1.6, which is fairly close to 1, 2. And the other eigenvector of the system has them in opposite directions, and so it's almost entirely mode 1, and the answer is about 96% mode 1 for the energy, and about 4 or 5% for mode 2 for the energy. Right, so we've covered energy in some detail. We've done the solution of all modes. So the two left things that I have to do on normal modes, and I will do one of them now, are dynamical inhomogeneous problems and normal coordinates. I think I'll do the dynamical inhomogeneous problems first, because those are actually on the syllabus, and normal coordinates aren't. So we now want to look at the equation where we're actually driving this mass with some sinusoidal force and working out the motion for the remaining parts of the system. So the equation of motion, so now we want, so this is solution with sinusoidal driving force. So, so this is m d2x. I'll do this in the equal mass case. It doesn't make a lot of difference, I don't think. M d2x by dt squared equals minus kx plus f of t, where this applied force F has the form is some constant F times cos omega t. So this has the form of an inhomogeneous linear equation, because if we just get the stuff containing x onto one side, we've got m d2x by dt squared plus kx equals f cos omega t, and that's some constant vector. And the same principle, so we know immediately that the solution will consist of a complementary function plus a particular integral. And the complementary function is found by setting this to 0 and solving the normal mode problem that we've already solved. So I won't talk about that. I'll just talk about xpi. Xpi we get by guessing an appropriate form for x and substituting it and forcing it to work. And if you've got, if the inhomogeneous term varies as a cosine, then in general you'd expect you'd write down you'd expect some constant vector times cos omega t plus some other constant vector times sine omega t. This particular problem is a bit simpler because we have no first derivative term on this side, we only have a second derivative term. So when I differentiate this, we'll only get cosine terms from the cosine, and we'll only get sine terms from the sine. And on the other side, we've only got cosine terms, so we don't actually need the sine term. So we'd need the sine term if we had a first derivative, which would turn a cosine into a sine and vice versa. So we don't need that term. So I'm just going to substitute ax equals a cos omega t. And if I do that, I get minus m omega squared a cos omega t. That's m times the second derivative of that, the second derivative being minus omega squared, plus k a cos omega t equals f cos omega t. And so that tells us that we've got the right solution because the time dependence now cancels. And we're left with k minus m omega squared I times a equals f. And obviously, if we'd had an unequal mass case, this mi here would get replaced by the mass matrix capital M. So in fact, the two cases work in exactly the same way at this point. Now, the last time we had an equation like this, we constructed this matrix to be singular because we were doing an eigenvalue problem. This is not an eigenvalue problem. This matrix is not singular unless omega is one of the modal frequencies. So we will find that if omega is one of the modal frequencies, this particular integral doesn't work. But so for omega not equal to omega I, then the matrix is non-singular, and we get A equals k minus m omega squared I inverse times f. And when you compute that inverse, you will find effectively on the denominator you'll get stuff which involves the difference between omega squared and the normal modes, and so the solution quite explicitly fails when we have a normal mode, when omega is a normal mode frequency. But for all other frequencies, that's the answer, and then it's just turning the handle to find what to invert that matrix, and so x is a cos omega t. So that's the solution for the particular integral. So we get all the masses oscillate with at the driven frequency, but with different amplitudes given by the components of this vector A, which is computed from the inverse of that matrix. What if if omega is omega I, Well, what happens if you drive a, so what's the resonant frequency? Dong, 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 dong. So if I drive it by oscillating the support point, what happens is that the amplitude grows and grows and grows. So we'd expect, so if omega equals omega I, then a good guess would be x equals a t cos omega t plus b t sine omega t. And I won't go into that now, but because we wouldn't have enough time to complete it. But if you work through that as an appropriate particular integral, I think you'll find that I think in fact you get this solution, but not that solution. But I can't remember. But I haven't got that in my notes, and I'm not going to do it without notes again. So the only remaining thing that I was going to say about normal modes before moving on to the transition to waves was about normal coordinates. Right back in the first lecture, we observed that for problems with the additional symmetry k11 equals k12, if we had a d2 x by dt squared is minus kx. If this k here was of the form k11, k12, k12, k11, then we could simply add or subtract the two equations and get an uncoupled equation for x1 plus x2 and x1 minus x2. And I said, so x1 plus x2, so I'll call that q1, and q2 equals x1 minus x2 are examples of normal coordinates. And also we did a little puzzle in the first lecture of figuring out that if we invented some completely off-the-wall values for doing the first equation, for multiplying the first equation and the second equation, we could actually find values, but they were just the values you'd never think of. And then a bit later on, it turned out that those values looked awfully like the components of the eigenvector. So that suggests that a sensible thing to do would be to multiply on the left by one of the eigenvectors. So once you've found the eigenvectors, we can revisit normal modes, and we get normal coordinates, and we get something like this. So we multiply on the left by C1 transpose. So we get M C1 transpose d2x by dt squared equals minus C1 transpose k C1. So k x. So these are just constants, of course, so I can take them inside the derivative, so I could write that as m d2 by dt squared of C1 transpose x. And on the left, well, we observe that if I just look at that constant, if I take the transpose of that, that is x transpose k C1 transpose, which is x transpose k C1 is lambda C1 transpose, which is C1 transpose x times lambda. And so this side of the equation has become lambda C1 transpose x. So if I define now Q1 equals C1 transpose X. The equation I've just derived is m d2 by dt squared Q1 equals, minus sign missing, minus lambda Q1, or d2 Q1 by dt squared is minus lambda over m Q1, an SHM equation. So Q1 satisfies an uncoupled simple harmonic motion equation and is a normal coordinate. So Q1 is a normal coordinate. So the normal coordinates are found by doing C1 transpose on the equation of motion, and in the uncoupled mass case, that gets you C1 transpose X. In the unequal mass case, you'll get the extra mass matrix here, and the normal coordinates are C1 transpose times the mass matrix times X, because every dot product in the unequal mass case has the m in it. And so in the unequal mass case, in the general case, we'd have an m in there, and it wouldn't appear here. So that's not why normal coordinates are easy in some problems, because the eigenvectors for this kind of problem are easy, and they're hard in problems where the eigenvectors are hard. So that normal coordinates are not a fantastic amount of use, because the only time they come into their own, you hardly need them anyway. So that's not a very strong recommendation, which is perhaps why they're not on the syllabus. So let's leave it at that for today. Tomorrow, next week, I will talk about the transition to waves and then move into wave phenomena on Monday and Tuesday next week. Right.
I'm up next.
What are you doing?
What?
What are you doing?
Vector calculus.
Oh, right, right.